All right, so hi everybody, welcome back. Today we're going to be starting a new lecture. This lecture covers a number of different topics, including heat, temperature, and the laws of thermodynamics. So the content of this lecture comes from a number of different places in the textbook. So we have sections 1 through 2 of chapter 18, and then most of chapter 19. We're going to cover sections 1 through 6, and then also section 10. Now this is going to be the last lecture of the semester. So once we get through this, it should take about 3 videos to get through this. We'll just be reviewing for the final exam. So let's get started with our first topic, which is the microscopic interpretation of temperature. So here we're going to try to understand what temperature is. What does it mean to say that an object has a certain temperature in terms of the microscopic motions of the atoms and molecules that make up that object? So we'll start by focusing our attention on gases. It turns out that it's much easier to analyze the microscopic motions of a gas compared to, let's say, a liquid or a solid. So we'll start by analyzing gases, and then we'll generalize what we've learned to liquids and solids later on. So the kinetic theory of gases describes a gas as a collection of a huge number of microscopic particles which are in constant and random motion. So this is the basic picture you should have in your mind when it comes to the kinetic theory of gases. If this is a box of gas, on the microscopic level, it's just a collection of a huge number of tiny little particles which are too small to see with the naked eye, but they're there, and they're moving around in a chaotic and random way. They're constantly bumping into each other, bumping into the walls of the container, and so overall the motion is pretty complex. And so as a historical note, this theory was developed back in the mid-1800s, which was long before the discovery of atoms. So nowadays we know that all matter, everything we can see and touch around us, is composed of atoms. But back then, that wasn't a settled issue. There was actually some controversy. The idea was if you take some chunk of matter and you divide it into smaller and smaller pieces, are you going to reach a smallest piece, a fundamental building block of all matter? Or can you just keep dividing it indefinitely? That was an argument that people had at the time, and again, there was no uniform agreement about this. So when the kinetic theory of gases was developed, the assumption was that a gas is composed of tiny little particles, but that wasn't really a settled issue at the time. But now we know this is the correct way to think about it, because we know that a gas is made up of atoms. So even though these motions that we see for these individual particles are very complex and very chaotic, the surprising thing that comes out of the kinetic theory of gases is that the large-scale picture of the gas, in terms of what is the pressure, what is the temperature, how much volume does the gas occupy, things like that, turns out to be really simple. So we have this really complicated description on the small scale of all these randomly moving particles, which gives us a really simple description on the large scale, again, in terms of pressure and temperature and things of that nature. So the next thing I'm going to show you is the ideal gas law, which you may have already seen if you've taken chemistry before. But before we actually state what the ideal gas law is, I want to tell you some of the assumptions we're making when we use the ideal gas law. So the first assumption is that molecules move in random directions. In other words, there's no preferred direction of motion. They're not moving more in the x direction than they are in the y direction or in the z direction. There's no preferred direction. It's completely random. And there's some range of speeds. Not everything is moving at the exact same speed. The second assumption is that the molecules are far apart. Specifically, what we mean by this is the separation, the distance between molecules is much, much bigger than the diameter of each one of those molecules. So if we look at the molecule and we sort of treat it like a little sphere, it has a certain diameter. That diameter is much smaller than the distance to the next molecule that neighbors it. Okay, third assumption is that the molecules obey Newton's laws of motion. So if a molecule collides with the wall of the container, or if two molecules collide with each other, or if anything else happens, we can analyze that using Newton's laws of motion. So the next assumption we'll make is that long-range attractive or repulsive forces between molecules can be ignored. So fundamentally, every atom and molecule is composed of protons, neutrons, and electrons. And protons have a positive charge, electrons have a negative charge. And you may know that positive and negative charges tend to attract each other, whereas like charges, so if you have two positives or two negatives, they'll repel each other. So because of that, you can get these forces between molecules, either attracting or repelling each other. But what we're going to do here is ignore those types of forces. And then the last assumption we make is that all collisions, whether they be with the wall of a container, so a molecule hits a wall of a container and bounces off, or between two molecules can just bump into each other, we're always going to assume that those collisions are perfectly elastic. And remember that an elastic collision means that no energy is lost during that collision. So if we have two molecules that meet and bump into each other, they have the same exact amount of energy before they collided as they do after. That's going to be the assumption. Okay, and with all that said, let's take a look at the ideal gas law. The ideal gas law says that PV is equal to N times K times T. So let's go through what each one of those variables represents. P is the absolute pressure of the gas. V is the volume that's occupied by the gas. N is the total number of molecules of gas we have. So this is going to be a very large number in general. K, and we actually call this KB, to be clear that this is a constant called Boltzmann's constant. This is equal to 1.38 times 10 to the minus 23. The units are joules per Kelvin. So this is a fundamental constant of nature. It's called Boltzmann's constant, and it goes right here in the equation. And then T is the temperature, but it's the absolute temperature of the gas. So we cannot be using the Celsius or the Fahrenheit scale for this temperature. That won't work. This only works if we're using an absolute temperature scale, which is going to be the Kelvin scale for our purposes. Okay, so that's what the ideal gas law says. Let's do a few examples to really get this down. So example number 1. A gas with an initial temperature of 23 degrees Celsius is in a sealed container with rigid walls. So that means the volume can't change. The volume is just fixed. If the pressure doubles, what will the new temperature be? So let's try to work this one out. Okay, we'll start with the ideal gas law. PV is equal to N times Boltzmann's constant times T. Now in this scenario, N, the number of gas molecules, KB, Boltzmann's constant, and also V, the volume, are held constant in this process. So it's only the pressure and the temperature that change. So a little trick you can do using the ideal gas law is to take everything that's constant and put it on one side of the equation. So let's divide through by T. So we have P divided by T on the left side. And let's also divide through by V. So we have N times KB divided by V on the other side. So if we take a look at this quantity right here, this is just one big constant, which is telling us that the ratio of pressure to temperature is held constant. So what we can say is P initial divided by T initial equals P final divided by T final. We don't need to know anything about the other variables. And what we want is T final. We want to know what the final temperature is. So if we solve for it, T final equals T initial times P final over P initial. Okay, so we're given that the pressure doubles. That means P final is 2 times P initial. Okay, that's how we say the pressure doubles. What do we know about T initial, the initial temperature? Well, it's 23 degrees Celsius, but we can't just plug that in. We need the temperature in Kelvin in order to make any calculations here. So if you remember, we can take the temperature in degrees Celsius and then add that to 273 to get the temperature in Kelvin. So the temperature in Kelvin is 296. Okay, so now we can just plug in the numbers. T final is equal to T initial, which is 296 K. P final is 2 times P initial, so I'm going to put that on top. And then we just have P initial on the bottom, so it doesn't even matter what that initial pressure is, just that we've doubled it. So if we take 2 times 296, we get 592 K. And as a final step, we can take that and then we can convert it to Celsius. So if I take 592 and then subtract 273, now we're back in degrees Celsius. And the answer would be 319 degrees Celsius. But again, I just want to warn you, when we do a calculation using the ideal gas law right here, the temperature has to be in Kelvin. If you plug in the temperature in Celsius, so that would just be 2 times 23 degrees Celsius, you get the wrong answer, okay? So you have to use the absolute temperature in Kelvin in order for this to work. Okay, here's another example. CO2 gas is kept in a container under 3 atmospheres of absolute pressure. The volume of the gas is 4 liters, and the temperature is 155 degrees Celsius. The question is, how many particles of gas are in the container? So in this one, we're solving for N. So once again, we'll start with the ideal gas law, PV equals NKT. And if we want to solve for N, let's divide out KT on both sides. That would equal PV divided by KT. So this seems like a pretty straightforward plug and chug, but before the calculation goes on, we need to get the units straight. We need to convert everything to SI units. Okay, so we'll start with the temperature. We need the temperature to be in Kelvin rather than degrees Celsius. So if we have 155 degrees Celsius, that's the same as 155 plus 273 in Kelvin. And so if you work that out, it's 428 Kelvin. Okay, let's take a look at the volume. The volume is given in liters, but the SI unit for volume is a cubic meter. So in every 1 cubic meter, we have 1,000 liters. So a cubic meter is about how much liquid can fit inside of a bathtub, and a liter is like your water bottle. So it's about 1,000 of those per cubic meter. So this would be 4.00 times 10 to the minus 3 cubic meters. That's the volume that we're dealing with here. Let's also take a look at the pressure. So the pressure is given in atmospheres, but we know that for every 1 atmosphere, we have 1.013 times 10 to the 5 pascals. So this works out to 3.039 times 10 to the 5 pascals. Okay. Now there's one more thing about the units that I want to show you. Remember, a pascal is a unit of pressure, so it's a force divided by an area. The force is given in newtons, and the area is given in meters squared. So a Pascal is a Newton per meter squared. I could also write this as a Newton times a meter on top divided by meters cubed on the bottom. Okay, I'm just multiplying on the top and bottom by units of meters. But you'll also remember that a Newton times a meter is equivalent to a joule. So in other words, a Pascal is equivalent to a joule per cubic meter. Okay? So this is going to come into play when we actually plug the numbers in, because again, N is equal to PV divided by KT. So the pressure is 3.039 times 10 to the 5 pascals, but I'm going to write this as joules per cubic meter. Then I'm multiplying this by the volume, which we said earlier. It's 4.00 times 10 to the minus 3 cubic meters. So notice, cubic meters cancels out. Okay, then we divide by Boltzmann's constant. That's 1.38 times 10 to the minus 23. The units are joules per Kelvin. So now we can see that joules cancel out here and here. And then we multiply that by the temperature, which is in Kelvin, 428. Notice how the units of Kelvin now cancel. All units have canceled. So we're not left with a quantity with units, we're just left with a number, which makes sense because we're talking about the number of particles in the container that doesn't have units attached to it. So this would be 2.058 times 10 to the 23. We're going to keep 3 sig figs on that, so 2.06 10 to the 23 particles. So again, the number of particles is very, very large. So next we're going to go through a derivation, and just to warn you, this is a pretty long derivation, but it leads to a really important result. So I want you to follow along with me as we go through this derivation so you can see where the result comes from. So first, we're going to consider a box which has dimensions L by L by L. So here, let's draw the box. It's in the shape of a cube, and the length along each side of the cube is L. So this length is L, this is L, and then also this is L, okay? Now, the box is not empty. It actually contains a bunch of gas particles. Let's say there are N gas particles, okay? So some very large number of gas particles is filling this box. Okay, so what we're going to do is focus on one particle, and in particular, a collision of that particle with one of the walls of the container. So we're going to focus on the collision of a particle with a wall of the box. Okay, so let's draw one particle colliding with one of the walls of the box. So we'll draw the x-axis going to the right, the y-axis going up like this. This will be the wall along the y-axis. So we'll have a particle, mass m, coming in, approaching the wall with some velocity, which we'll call v initial, and then bouncing off the wall with a velocity which we'll call v final. Now, as always, what we can do with these velocities is break them into x and y components. So let's show the x and y components of the final velocity and the initial velocity. So let's label the y component of this initial velocity as Vy. Now, let's consider the force that the wall exerts on this particle. The wall is pushing on the particle just to the right along the x direction. There is no force in the y direction. It's only in the x direction. And for that reason, the velocity in the y direction isn't going to be changed by this collision. So the final velocity in the y direction is still Vy, same value as before. What changes is the x velocity. So before the collision, the particle is moving in the negative x direction. So we'll call that velocity minus Vx. And in the final state, the particle is moving in the positive x direction, so that will carry a positive sign. But that will just be positive Vx, because remember, the collision is elastic. It has the same exact amount of energy before as it does after colliding with the wall. So basically all that happens here is the y velocity stays the same and the x velocity flips a sign. So with that picture in mind, let's calculate the average force from the wall on the particle. So you should remember from chapter 9 how to do this. The average force during a collision like this is equal to delta p, the change in momentum, divided by delta t, the time interval. Now in this case, we can only focus on the x direction because there is no change in momentum in the y direction. And by the way, we put a little bar on top of the f like this to indicate that we're talking about an average value. That's what the bar means. Okay, so let's first think about delta px. That's the change in momentum along the x direction because of this collision, which of course would be the final value minus the initial. Okay, well, what's the final momentum along the x-axis? That's going to be the mass of our particle times the final velocity along the x-axis, which if we go to the picture, is positive Vx. And then we subtract the initial momentum along the x-axis, which is the mass of the particle, times the velocity initial, which is minus Vx. So this is just 2 times m times Vx. Okay, so that takes care of delta px. What about delta t? What's the time interval? Well, we're going to let delta t be the time between collisions with the wall. So each time there's a collision with the wall, this is the change in momentum delta p, but delta t is how long you have to wait between different collisions with the wall. So to work this out, we'll simply use the definition of speed, which is distance traveled divided by time. Okay? And if we're talking in particular about Vx, okay, the velocity along the x direction, and delta t is the time on the bottom, how far does a particle have to travel? What's the distance that corresponds to that? So let's really think about this. Let's say the particle collides with this wall on the left side over here. How long does it take before that particle hits the wall again? Well, it's basically going to have to travel to the other side of the box, collide off of this wall, and then it will come back before it collides with that same wall again. In other words, it has to travel 2 times L, twice the length of the box, between collisions with a given wall. So Vx is 2 times L divided by delta t, or we can say delta t is 2 times L divided by Vx. So if we plug all that into our expression for the average force, we have delta px, which we just said is 2 times m times vx, divided by delta t, which we just said is 2 times L, divided by Vx. So to simplify, cancel out the factor of 2's, we have m times Vx squared divided by L. So to be clear, that's the average force that the wall exerts on one of the particles during a collision. But in reality, we don't just have one particle, we have a whole bunch of them. So next, let's consider the average force on a wall due to all of the particles. So this is pretty straightforward. If this is the force from one particle, then the total force from all of the particles should be a big sum, where each term in the sum looks like m times Vx squared divided by L. I need a term like that for every single particle. So the common factor we'll see is m divided by L. That can just be pulled out to the front. And then for the first particle, I'm going to have v1x squared. For the next particle, I'll have v2x squared, so I have to add that. And then keep going until I've included all of the particles. So this is, again, a giant sum over all of the particles. The last one would be vnx squared like this. Okay, so if I sum over all of those forces, I get the total force due to all of those particles. Okay, so let's take a closer look at how we can re-express that. We'll start with the definition of an average. So if I have a quantity Vx squared, how do I take the average of that? Well, I take Vx squared and put a little bar on top to denote that I'm talking about an average. But of course, I have to add up all the values. I have to add up v1x squared plus v2x squared plus ... Add them all up until we get to the last one, vnx squared like this. But then I have to divide by n. So add up all the values, divide by n. That's the definition of average. And that kind of looks like what we have in the brackets up here. Okay, the next thing we'll note is that the magnitude of a velocity, which is what we also know as the speed, is given by the Pythagorean theorem. So if I want the speed, v squared is going to be vx squared plus vy squared plus vz squared. Okay, that's how I go from x, y, and z components of a velocity to the speed. But this equally holds true if we're talking about averages. So if I put a little bar on top of each one of those terms to denote an average, it still holds true. Okay, the next fact that we're going to bring in is that there's no preferred direction of motion. Okay, so it's not like the particles move faster in the x direction than they do in the y direction or the z direction. On average, the particles are moving in the same, just as fast in the x, y, and the z directions. So I'll denote that by saying Vx squared average is equal to Vy squared average is equal to Vz squared average, right? There's no preferred direction. They're all on equal footing. So if we actually take what's on the second line, where average speed squared is equal to Vx squared plus Vy squared plus Vz squared, if x, y, and z are all the same, then I can say that the average speed squared is just equal to 3 times Vx squared average. So if we go back to the top of the page and look at this expression right here, the term in brackets, okay, that's basically summing over Vx squared for all the different particles, which is pretty much what we have over here in our expression for the average of Vx squared, except we have that big sum times 1 over n. So basically what I'm saying is if we want to know what this big sum v1x squared plus v2x squared plus ... vnx squared, that can be written as n times vx squared average, okay? So we can just think about the average rather than what each individual particle is doing. But from what we just found over here, we can say that the average of vx squared is just a third of the average speed. So then what we have in brackets can equivalently be written as 1/3 times n times the average speed squared. So now we're going from x velocity to speed by introducing this factor of 1/3. Okay, so the next thing we'll do is plug that into our formula for F total. So again, that's m divided by L times the term in brackets, which we just determined was equal to 1/3 times n times average speed squared. So the next thing we're going to do is introduce pressure. Remember, pressure is force per unit area, where what we've found already is the force of all of these different particles hitting one of the walls of the container. That's the F. The A, the area of each of those walls, is equal to L squared. So the pressure of the gas is going to be m divided by L times 1/3 times n times V average squared divided by L squared. And if we kind of write this in a more simple way, we have 1/3 times 1/L to the third power now times n times m times v squared average. Okay, I'm going to write this in a slightly different way. I'm going to pull out a factor of 2 to the front, so this is now 2/3, 1/L to the third times n. And then since I pulled out a factor of 2, I need a factor of 1/2 to balance that out. We have 1/2 times m times v squared average. So that thing in parentheses, 1/2 mv squared, should look really familiar. That's what we call the average kinetic energy. And I'll call that K bar. That's 1/2 times m times v squared bar. Another thing we can notice is the volume of the box. That's just L to the third power. So what I'm saying is the pressure is 2/3 times n divided by V, the volume of the box, times average kinetic energy, K bar. And I can rearrange that to say the average kinetic energy, K bar, is equal to 3/2 times P times V divided by N. Okay, just take what we found earlier, solve for K bar. The next thing I'm going to bring into the equation is the ideal gas law. Remember, this says PV equals N times KT. Now let's be careful. I'm going to label this as KB for Boltzmann's constant, not to be confused with K bar, which is the average kinetic energy. But at any rate, PV divided by N, which is what we see in our expression here, is just equal to KB times T. So average kinetic energy, K bar, is equal to 3/2 times Boltzmann's constant times the temperature. And that's the big result that I wanted to derive for you, because it's a relationship between the average kinetic energy of the molecules that make up the gas, and it relates that to the temperature. And everything else is just constants. So what this is telling us is the temperature is just directly proportional to the kinetic energy that the molecules have. The higher their kinetic energy, the higher the temperature. So what we've proven is that for an ideal gas, K bar is equal to 3/2 times KB times T, where K bar is the average kinetic energy of the gas molecules, KB is Boltzmann's constant, and T is the absolute temperature of the gas. We measure this in the Kelvin scale. Now, this actually applies more generally. In general, the average kinetic energy of the molecules in a system is directly proportional to the absolute temperature of that system. So this average kinetic energy and the temperature are just directly proportional to one another. That applies to solids, liquids, as well as gases. And that is our microscopic interpretation of temperature. The average kinetic energy of the molecules that make up an object is directly proportional to the temperature of that object. And this establishes a really important connection between the microscopic and the macroscopic realms. What we perceive as hotness or coldness, what we perceive as the temperature of the object, is just a direct result of the random motions of the molecules in that object. So to get a better sense of this, let's take a look at this animation, which is going to show us a simulation of an ideal gas. So we can see these molecules are in constant and random motion, okay? And if I were to track the motion of any one of those molecules, it would look pretty complicated because it's constantly colliding with the walls of the container. It's constantly colliding with other molecules. But I can talk about the average kinetic energy of those molecules, and that would just be some number, okay? So that number is directly proportional to the temperature of the gas. So if I increase the temperature of the gas, if I make it hotter, that means the molecules are simply moving faster. They have larger kinetic energies on average. And if I were to cool down the gas, make its temperature drop, then what I would be doing is slowing down those molecular motions. These gas molecules would be moving slower on average. Okay, that's the connection that we're establishing here. And that brings us to RMS speed. Now, RMS stands for root mean square. And the root mean square is a type of average. This is how you calculate the root mean square of any sort of quantity. First, you square all of the values. Then you find the mean of all of those squared values. And then you take the square root of that. That's the definition of RMS. So how does this relate to what we were just talking about? Well, remember K bar, the average kinetic energy, is equal to 3/2 times KB times T, where this is Boltzmann's constant KB. But on the left side, what we have is the average kinetic energy, which I can write as 1/2 times m times v squared bar. So this is the average of v squared here, which gives us the average kinetic energy. That equals 3/2 times KB times T. So we can simplify this a little bit. We can cancel out a factor of 2 here and here. We can divide out m right here. And then we can take the square root, which gives us VRMS. VRMS is equal to the square root of 3 times KB times T over m. So we can think of this as a sort of average speed of the molecules, defined in this way that I showed you up here. So let's do an example. What is the RMS speed of N2 air molecules at room temperature? That would be 20 degrees Celsius. So N2 is just a molecule that consists of 2 nitrogen atoms. Okay, that's the molecule that's most abundant in Earth's atmosphere. And then as a follow-up, what about O2 molecules in the air? These are the molecules that we need to live, consisting of 2 oxygen atoms. Okay, so to do the calculation, we need to know the mass of each one of these molecules. So for N2, the mass is 28 AMU. This stands for atomic mass units. It's a way of measuring very small masses. 1 AMU is equal to 1.66 10 to the minus 27 kilograms. So we can convert this to kilograms. Now, O2 molecules are 32 atomic mass units, so a little bit more massive than the nitrogen. And again, we can convert that to kilograms using this factor. So let's work it out. So we'll start by converting the temperature from Celsius to Kelvin, because the temperature has to be an absolute temperature in the Kelvin scale for this to work. So we have 20 degrees Celsius. If we take that 20 degrees Celsius and we add 273 to that, we now have the temperature in Kelvin, which would be 293 K. Okay, so let's first take a look at the N2 molecules. All right, the mass of those molecules would be 28 times 1.66 times 10 to the minus 27 kilograms. And so the RMS speed of those molecules would be the square root of 3 times kb times t divided by m. So we have the square root of 3 times 1.38, 10 to the minus 23. Joules per Kelvin is Boltzmann's constant. The temperature, 293 K. And then divide that by 28 times 1.66 times 10 to the minus 27 kilograms. If you crunch these numbers, it's about 510 meters per second. So the N2 molecules that are flying around you right now are moving on average at about 510 meters per second. If we do the same calculation for O2, which has a slightly larger mass of 32 atomic mass units, which would be 32 times 1.66 times 10 to the minus 27 kilograms, well then VRMS in that case would be the square root of 3 times Boltzmann's constant is 1.38, 10 to the minus 23 joules per Kelvin. Same temperature, 293 K. What's different is the mass. So now we have 32 times 1.66, 10 to the minus 27 kilograms on the bottom. And let's just take a quick look at the units here. You can see that units of Kelvin cancel. And what we're left with is the square root of joules divided by kilograms. But I want to remind you that a joule is a kilogram times a meter squared per second squared. Kilograms cancel, take the square root, it's meters per second, okay? Anyway, if you crunch these numbers, you're gonna get about 480. So the oxygen molecules, O2, are moving slightly slower because they have more mass, okay? They have the same kinetic energy as the N2 molecules, but because they're more massive, they move slightly slower. So more massive molecules move slower on average. Okay, that's the idea. And I want to just reiterate that VRMS only represents a typical or average speed for a particle in your ideal gas. In reality, there's going to be a whole range of different speeds within that gas. And so that's where the Maxwell-Boltzmann distribution comes in. Now, this is not something we're going to learn about in any mathematical detail. I'm basically going to just sort of mention this and move on. And this is something you may see if you take more advanced physics. But the Maxwell-Boltzmann distribution describes the probability that a randomly selected particle in your gas is going to have a certain speed. So we can actually plot this out by putting probability on the vertical axis and then speed on the horizontal axis. So where we have very large values of the probability, that means you're going to have a lot of particles with that speed. But where the probability is very low, you won't find that many particles with that speed. So the curve generally looks like this. At low speeds, you're going to see very low probability, so there aren't that many particles moving super slow. But then it starts to go up, and then it peaks somewhere. So this is the most probable speed. This is our VRMS up here. and then it begins to go back down. There aren't that many particles with super high speeds either. So everything is kind of clustered in this area. Now, this is what we call our distribution, that little curve that shows us the probability of getting different speeds. If we increase the temperature, the distribution is going to peak. The peak of the distribution is going to be at a higher speed. So if this curve is for T1 and this curve is for T2, we know that temperature 2 is bigger than temperature 1 because it's describing faster moving particles. Okay, on average, the particles are moving faster. Another thing that happens when you increase the temperature is the distribution gets wider. So there's a wider range of speeds that you'll see as the temperature gets higher. So again, this is something you might see in a more advanced physics class. So let's move on from that and talk about something called thermal equilibrium. And so to understand what thermal equilibrium is, let's take a look at an example. Let's consider two blocks which start off with different temperatures. So we have a hot block, which is at 300 degrees Celsius, and a colder block at 0 degrees Celsius. But what we do is we place these blocks in contact with one another so they can exchange heat, basically. So what's going to happen over time is the hot block's temperature is going to go down and the cold block's temperature is going to go up. And that's going to continue to happen until they reach the same final temperature. So when this process is complete, they're both at the same temperature now, which is somewhere in between the two starting temperatures. So for instance, they could both be at 150 degrees Celsius when this process is over. That final state that we reach is called thermal equilibrium. Okay? Now before thermal equilibrium, we have heat flowing from the hot block to the cold block. And so once the two blocks reach the same temperature, there's no longer heat flowing between them. And this is what we call thermal equilibrium. We say in this final state, the two blocks are in thermal equilibrium with each other. So what were some of the early ideas about thermal equilibrium? How did people try to explain this in the early days of physics? So one idea that was very popular for a long time was something called the caloric. So the idea was you can explain how certain objects are hot and other objects are cold by postulating that there is this substance called a caloric. And objects that are hot have a lot of caloric sort of attached to them. Colder objects have less caloric. Okay, that's the idea. The caloric was also thought to be sort of like a fluid. It can flow. It can move from one object to another. It was also thought to be self-repellent. So if you have a lot of caloric concentrated in one area, it's going to want to spread out because it repels from itself. So naturally, it's going to flow from hot objects to cold objects. This was the idea that was very popular for a long time to explain, again, the phenomenon of heat and temperature. But by the mid-1800s, this theory became obsolete. It became very clear that there is no such thing as the caloric, and there's no physical substance that moves around from hot objects to cold objects. There's something a little bit more subtle going on. Okay, the caloric theory is not correct. So what is the correct way to think about this then? What is the modern understanding of thermal equilibrium that we should have? Well, let's think back to the result we derived just a little while ago. The average kinetic energy of the molecules that make up an object is directly proportional to that object's temperature. So if we compare these two blocks, one at a higher temperature than the other, that also means that the hotter block is composed of atoms and molecules that are jiggling around faster than for the cold block. Okay, that's the difference between them on the microscopic level, is how fast their molecules are moving. But if we put them in contact with each other, if we allow the surface of one block to touch the surface of the other, now they can exchange energy. Energy can be moved from one block to the other. How does that happen? Well, the hot block, if we look at this surface of it, has molecules jiggling back and forth like this, and so does the cold block. So those molecules are going to be colliding with one another. And in those collisions, the hotter block is losing energy. Its total energy is going down. Its temperature, as a result, is going down. Whereas the colder block is gaining energy from those collisions. And as its energy increases, then the temperature goes up. And this is going to keep happening. They'll continue to exchange energy like this until the point when the average kinetic energy of the molecules in both blocks is the same. Okay, when the molecules have the same average kinetic energy, the two blocks now have the same temperature. And that's what we call thermal equilibrium. So we don't need some sort of mysterious substance called a caloric to make this work. We can understand thermal equilibrium just in terms of the random motions of the atoms and molecules that make up an object. And the big picture of this is, as time goes on, energy goes from being concentrated in hot regions to being more spread out evenly when thermal equilibrium is reached. Okay, that's the idea. So here's a really simple example. If we put ice cubes into a glass of liquid water, we can see that the ice cubes will melt over time. And the reason for this is that initially, the molecules of water in these ice cubes have very low kinetic energy. That's why they have a low temperature. Whereas the liquid water that surrounds it is composed of water molecules that are moving much faster. They have higher kinetic energies. And because they're in contact with one another, they can exchange energy, they'll do that. And over time, the ice cubes are going to gain energy, and this liquid water that surrounds it is going to lose energy. And so they reach thermal equilibrium. They eventually reach the same final temperature. And that's what we see happening as these ice cubes melt into the water. So before we go any further, I just want to clarify some terms. So we have internal energy, temperature, and heat. I just want to make sure everyone understands the difference between these three terms. So internal energy is the energy that an object has due to the random motions of the atoms and molecules it is made out of. So if we take this block as an example, if the block is moving around and I can see that the block as a whole is moving around the page, I would say that it has kinetic energy. If I were to take the block and raise it to a greater height, then I would say it's gained some potential energy. Internal energy is independent of all that. It's something else. So even if the block appears to be not moving at all, okay, it appears to have no macroscopic motion, it still can have internal energy because if we zoom in and look at the individual atoms and molecules that make up the block, they're randomly jiggling around, even if the block as a whole is not moving anywhere, okay? So if we take the sum total of those microscopic motions of the atoms and molecules and add up all of those energies, that's what we call the internal energy of the block. So that's the idea. Now, temperature is what we typically think of as the hotness or the coldness of an object. But as we've seen, temperature is actually determined by the average kinetic energy of the atoms and molecules that make up an object. So if things are moving faster on average, then the temperature is higher. And then lastly, we have heat. Heat is given by the variable Q. Okay, so whenever you see Q, that corresponds to heat. Heat is a transfer of energy from one object to another due to a temperature difference. Okay, so heat is not energy, but energy moving from one place to another because of a temperature difference. That's the idea. So if we have two blocks at different temperatures, we have temperature T1 for this block, we have temperature T2 for this block, and T1 is bigger than T2, we'll see that energy is being transferred from the hot block to the cold block if they're allowed to be in contact. So we show this as an arrow. Q is going from the hot region to the cold region. That's how we show this. And that takes us to the next section of the lecture, dealing with heat capacity, specific heat, and latent heat. So let's define these things and see why they're useful concepts. Starting with heat capacity. So I want you to think about the general idea of heating something up or cooling something down. And we're going to assume for now that there's no phase change happening. So for example, there's no melting from solid into a liquid phase. We're just thinking about heating something up or cooling something off with no phase change. So if energy flows into a system, then its temperature is increasing. If energy flows out, then its temperature is decreasing. And we can put this in a more mathematical statement by saying energy flowing into a system means Q, the heat, is positive. Energy flowing in corresponds to positive heat. That also corresponds to a positive temperature change. The temperature is going up. Delta T is positive. If energy is flowing out, that corresponds to negative heat, so Q is negative, and that corresponds to a temperature decrease. Delta T is also something negative. So typically what we're going to find is a linear relationship between Q, the heat flowing in or out, and delta T, the temperature change. So we can express this linear relationship in the following way. Q is equal to C, capital C, times delta T. Okay, so there's just a linear relationship between these two, and there's some sort of constant of proportionality here, and we call that the heat capacity. So the heat capacity, capital C, is the amount of energy that's required to change the temperature by 1 degree Celsius or 1 Kelvin. So that means the SI units for the heat capacity are joules per Kelvin or joules per degree Celsius. So let's see that in a little bit more detail. So we'll start with Q is equal to capital C times delta T. If we rearrange that, we can see that capital C is equal to Q divided by delta T. Capital C is our heat capacity. That's equal to Q, which is the heat. That is the energy flowing in or out of the system. Delta T is the temperature change of the system. So the heat capacity is just the ratio of the energy flowing into the system divided by the temperature change. So you can think of it as how much energy do I need to get the temperature to change by a given amount. So the units would be energy units on top, which are joules, and then temperature units on the bottom, which, well, they can be Kelvin or degrees Celsius. It turns out these are perfectly equivalent because if we're dealing with a temperature change, okay, a change in temperature, Kelvin and Celsius are equivalent. So obviously this is not true for an absolute amount of temperature, but it's only true for a change in temperature, for a delta T. Okay, so I want to remind you that the temperature in Kelvin is just equal to the temperature in degrees Celsius plus 273. Okay? So what if I had a temperature change then, which I'm measuring in Kelvin? Well, that would be the final temperature in Kelvin minus the initial temperature in Kelvin. Okay, final minus initial. But for T final, I can write this as T final in Celsius plus 273. And then I subtract T initial in degrees Celsius plus 273. So I'm basically converting the units in this step. But what we see is I have positive 273 and negative 273. Those just cancel out. So I'm left with T final in degrees Celsius minus T initial in degrees Celsius, which is delta T in degrees Celsius. So what we've shown is the temperature change, delta T, is equivalent whether we're talking about Kelvin or degrees Celsius. Again, this only works for a temperature change. And that takes us to specific heat. Now, the problem with heat capacity, capital C, which we just defined, is that it depends on the size of the system. For example, if I had 2 kilograms of ice, that would have double the heat capacity as just 1 kilogram of ice, even though I'm talking about the same material. So we want a way of talking about how easy it is to heat something up or cool something down that is independent of the size of the system. It just depends on the material that it's made out of. That's where specific heat comes in, and specific heat is given by lowercase c. So here's how it's defined. Mass-specific heat is the amount of energy required to change the temperature of 1 kilogram of a substance by 1 degree Celsius or 1 Kelvin, same thing. So the way we get specific heat, lowercase c, is we take the heat capacity, uppercase C, and then we divide out the mass. By dividing out the mass, we now have something that's independent of the mass, okay? So if Q is equal to uppercase C times delta T, we can see from over here that uppercase C is just lowercase c times m. So Q is equal to m times lowercase c times delta T. And this is the form we'll be working with most of the time, okay? So what does this equation say? Q, the heat flowing into or out of the system, is equal to m, that's the mass of the system, times lowercase c, that's the mass-specific heat of the material or the substance that our system is made out of. And delta T is, again, the temperature change. So for specific heat, we have a new unit. Instead of joules per Kelvin or joules per degree Celsius, this is actually joules per Kelvin per kilogram or joules per degree Celsius per kilogram. So we have this additional unit of kilograms in the denominator because we've basically divided out the mass. That's the idea. Okay, so specific heat, lowercase c, is given by heat capacity, uppercase C, divided by m. And of course, we saw earlier that heat capacity is Q divided by delta T. It's the heat divided by the temperature change. What we're doing here is we're basically dividing out the mass on top of that. So we have Q divided by m times delta T. So basically, this is heat flowing into the system divided by the mass and the temperature change. So if we're talking about water, for example, the specific heat would tell us how much heat has to flow into the system to get 1 kilogram of the substance to change its temperature by 1 degree Celsius. So thinking about the units here, again, we have energy units on top, joules, then mass units, kilograms, and temperature units, Kelvin on the bottom, or those temperature units can equivalently be degrees Celsius. So one specific heat that we're going to see come up a lot is the specific heat of liquid water, which is 4,186 joules per kilogram per degree Celsius. And how do we know that that's the correct value? How was this measured? Well, I'm going to tell you about a famous experiment performed by James Joule. And James Joule is the guy that our energy unit is named after. And here's how the experiment goes. We have this apparatus where we have weights that are hanging from a string connected to a pulley, and that string is wrapped around a shaft. And that shaft, if we follow it down, is connected to these paddles. So as the shaft turns, it makes these paddles turn inside a container of water. So what we do is we drop the weights, we let them fall to the ground. As they fall, they're going to get this shaft spinning and get these paddles churning through the water. and those paddles will be churning through the water for a while, but after some time passes, they're going to be brought to a stop because of the drag forces within the water. So as a result of that, the temperature of the water is going to increase. And here's the thing, we know exactly how much energy was added to the water, because we know at the start of all this, these weights were a certain height above the ground. So we can easily measure their potential energy. In this process, the potential energy of these weights is converted into thermal energy, that is energy of the water molecules as they jiggle around randomly in this container. So as a result of that, the temperature goes up. We can measure exactly how much energy it takes to get 1 kilogram of water to increase in temperature by 1 degree Celsius. And in his experiments, he consistently found that that amount of energy was 4,186 joules. So it takes 4,186 joules of energy to get 1 kilogram of water to increase in temperature by 1 degree Celsius. Therefore, this is the specific heat of liquid water. Now, with that in mind, let's do an example. How much energy is given off when 45 grams of liquid water cools from 65 degrees Celsius to 25 degrees Celsius? Let's work this out. So we'll start with Q equals M times lowercase c times delta T. Now, M is the mass of the water, which is 45 grams, or 45 times 10 to the minus 3 kilograms. C is the specific heat. For water, that's 4,186 joules per kilogram degree Celsius, like this. Delta T is the temperature change. So we end up in the final state at 25 degrees Celsius, starting at 65 degrees Celsius. So delta T is T final, 25 degrees Celsius, minus T initial, 65 degrees Celsius. And if you crunch these numbers, you'll see that it comes out to minus 7,535. The units we end up with are joules because kilograms cancel here and here. Degrees Celsius cancels here and here. We're just left with joules. And if we round this to 2 sig figs, we get minus 7,500 joules. Now, what does that negative sign indicate? The negative sign means energy is flowing out of the water, which makes sense. If the temperature is going down, energy is flowing out of it. That's indicated by the negative sign. So again, the specific heat of a material tells you how difficult it is to change its temperature. So if a material has a very large specific heat, that means it takes a lot of energy in order to get its temperature to increase by a certain amount. On the other hand, if a material has a low specific heat, then it's very easy to heat it up. It takes a very small amount of energy to get its temperature to change by a certain amount. Now, this table here lists a bunch of common specific heats. Each material has its own unique specific heat, and you can refer to this if you need to. There's also a table like this in the textbook in chapter 19. So in some of the problems on the homework, you'll have to look up a specific heat. You can do that here or in the textbook. And what we're doing by listing these specific heats is we're assuming that the specific heat of a material is constant, so it doesn't change in any way. In reality, specific heats can change somewhat depending on the temperature and the pressure of the material, but that's an effect we're going to ignore in this class. So we're going to assume specific heats are just constants. So here's a question for you guys to try out. How much heat is required to raise the temperature of an empty 20 kilogram aluminum vat from 10 degrees Celsius to 90 degrees Celsius? Okay, if the same vat were filled with 20 kilograms of water, how much heat would be required in that case? So to do this, you're going to need to know that the specific heats of liquid water and aluminum are 4,186 and 900 joules per kilogram per degree Celsius, respectively. So as a final calculation, we're going to make a comparison. How much energy is required to accelerate a 25,000 kilogram train car from rest to a final speed of 20 meters per second, which is about 45 miles per hour? So pause the video for a second, try to do these calculations, and then we'll go through it together. So let's start by thinking about the empty vat, which is made out of aluminum. So the heat that we need to add to the aluminum in order to get its temperature to go up is given by the mass times the specific heat times the temperature change. So I'm going to have the subscript AL just to remind us that we're talking about the aluminum here. Now the mass of the aluminum is 20 kilograms. The specific heat is 900 joules per kilogram per degree Celsius. And then the temperature change, we start at 10 degrees Celsius, we end up at 90. So 90 degrees Celsius minus 10, that's T final minus T initial for delta T. And if you crunch these numbers, you get 1.44, 10 to the 6 joules. And equivalently, we can write that as 1.44 megajoules. So M is the prefix for mega, which is 10 to the 6th power. Okay, now what if we have the vat filled with water? So the heat that needs to flow into that system, call that Q total, is the heat for the aluminum plus the heat for the water. So for the aluminum, we already have a number, so we'll leave that as is. For the water, that's going to be given by the mass of the water times the specific heat of the water times delta T for the water, H2O. So here's what we have. We have 1.44 times 10 to the 6 joules for the aluminum, plus the mass of the water is 20 kilograms. The specific heat is 4,186 joules per kilogram per degree Celsius. And delta T is the same. We end up at 90 degrees Celsius starting from 10. So again, that's our T final minus T initial. And this works out in units of joules to be 8.138, 10 to the 6. Or we can write this as 8.14 megajoules. So what we see is it's a lot harder to heat up the water because it has a much larger specific heat than the aluminum. Okay, and then finally, let's compare this to our train car. Here, we're talking about kinetic energy, which is given by 1/2 mv squared. So we have a half times the mass of the train car is 25,000 kilograms. The speed ends up being 20 meters per second, and we square that. This works out to 5 times 10 to the 6. We have kilograms, meters squared, and seconds squared, which is a joule. So this would be 5 times 10 to the 6, or 5 megajoules. So that might be a little surprising because you imagine this gigantic train, to get it to accelerate to this speed would take a lot of energy, and it does, but it actually even takes more energy to heat up this giant pot of water. Okay, that's what we see here. And that takes us to isolated systems. So an isolated system is any system that does not exchange energy with its environment. And this means a couple things. First, no heat flows into or out of the system, so Q is equal to 0 for the system as a whole. And also, no work is being done on the system by any sort of outside force. So W is also equal to 0. Now, the way you should visualize an isolated system is like this. Let's say we have two objects, number 1 and number 2, and that's the whole system, just those two objects. So we can draw a little boundary around those two objects. That's called our system boundary. And what we're saying is no energy is flowing into or out of that boundary. That's what it means for the system to be isolated. But let's say object number 1 is hotter than object number 2. It has a higher temperature. We know that heat is going to flow from 1 to 2. So Q1 is going to be negative, indicating that heat is flowing out of that hot object. It's losing energy. And on the other hand, Q2 is going to be positive because heat is flowing into that object. It's gaining energy. And when we take the sum of Q1 plus Q2, that's the total, what we get is 0 because there's no energy flowing into or out of the system as a whole. So for an isolated system, if we look at all the different parts of it, and we take Q total, which would be Q1 plus Q2 plus, you could have a whole bunch of Q terms if you have more than two objects, but when you sum them all up, you get 0. That's what it means to be an isolated system. So if you think about it, any energy that's lost from one object, because you have a negative Q over here, is gained by another object. So every negative Q is sort of balanced out by a positive Q. That's what it means to have an isolated system. So let's do an example where we put that idea to use. So a well-insulated container holds 567 grams of liquid water at 20 degrees Celsius. A 155 gram sample of aluminum is placed under a flame and heated to a temperature of 325 degrees Celsius. So we have a very hot chunk of aluminum. And then we place that into the container of water. The question we want to answer is, what is the final temperature of the water and the aluminum sample? So to do this, we need to know the specific heats. Again, for water, 4,186. For aluminum, 900 joules per kilogram per degree Celsius. So we're going to assume that no energy is lost from the water plus aluminum system during this process. So let's work it out. So as we said, for the system, Q total is equal to 0. But Q total can be broken up into the heat for the aluminum, QAl, plus the heat for the water, QH2O. When we add those together, we get 0. Now, the heat for the aluminum is going to be negative because it's going to be losing energy. The water is going to be heating up. It's going to be gaining energy, so that will be a positive term. When we add the negative and the positive heats together, we get 0. That's the idea. Now, for each one of these, the heat can be expressed as M times C times delta T. So we have mass of the aluminum, specific heat of the aluminum, times the temperature change of the aluminum. And then for the water, we have mass of the water, specific heat of the water, times the temperature change of the water. And that equals 0. So we can plug everything into this equation. The aluminum is 155 grams, or 0.155 kilograms. Specific heat is 900 joules per kilogram degree Celsius. For the temperature change, well, we don't know what T final is, so I'm just going to leave that as a variable. But for the aluminum, we do know the initial temperature, 325.0 degrees Celsius. Okay, and then for the water, the mass was 567 grams, or 0.567 kilograms. The specific heat, 4,186 joules per kilogram degree Celsius. And then we have delta T for the water. We don't know what the final temperature is. It's T final. But we know for the water, the initial temperature was 20 degrees Celsius. And all of that right there is equal to 0. Okay, so let's take stock of what we have here. We have 0.155 times 900 times T final. and then we have 0.567 times 4,186 times T final. So we combine those terms, and you'll get 2,512.96. If we think about the units for that term, kilograms will cancel. We'll be left with joules per degree Celsius, multiplying T final. Okay, in addition to that, I'm going to have 0.155 kilograms times 900 times negative 325 degrees. And then I'm going to have 0.567 times 4,186 times negative 20 degrees. You combine those terms together, you get something negative, which is 92,807. If you think about the way the units work out here, kilograms cancel and degrees Celsius cancel, so we just get joules, and that equals 0. So T final, what we're looking for, is 92,807 joules divided by 2,512.96 joules per degree Celsius. You see that joules cancel, degree Celsius goes to the top, and it turns out to be 36.93, but we're actually keeping 3 sig figs on that for a final answer of 36.9 degrees Celsius. So you take this chunk of aluminum, which is initially at a very high temperature, and drop it into the water, which is at room temperature. You wait, they reach thermal equilibrium, and once they do, this is the final temperature they reach, 36.9 degrees Celsius. So that's how you do this one. Now that's going to be it for this video. We'll continue on with this discussion in the next one. So I'll see you then. Until then, take care, be safe, be healthy. See you later.